A learner makes observations below after conducting an experiment using a photocell, right, with frequencies of incident light being above the threshold frequency, right, or what we sometimes call the cutoff frequency. Okay, and then these were the observations that he made. The first observation he made is that the photocurrent, right, increases as the intensity of the incident light increases. The second observation is that the emitter in the circuit registers a current immediately after the incident light is radiated on the cathode. And the third observation was that the photocurrent increases as the frequency of the incident light increases. Okay, interesting question. Right. Now, for multiple choice questions, you just need to be careful about what is actually given to you before you actually even try to decide, is this going to be A, B, C, or D? Okay, so now let's read this carefully again, right, and pull out the important information. Okay, so the important part about what this learner is doing is that the light that he's using, right, so the incident light, okay, they're telling us that the incident light already, right, that he's using has frequencies that are above the threshold frequency. Okay, so now your theory must come in here. Okay, so what we're saying is that he's using, okay, light such that the frequency of the light is greater than the threshold frequency. Okay, now that means that if the frequency of the light is greater, right, than the threshold frequency, it means that the light is able to emit the photoelectrons, right, which then leads us to the current in the circuit, right, or what we call the photocurrent. Okay. All right, now there's two statements here that talk about this photocurrent, so we need to now decide which one of the statements is the correct one, okay? Because the only difference in the statements is that the one says the photocurrent increases as the intensity increases, right? And the other one says the photocurrent increases as the frequency increases. So we now need to decide which one actually increases the photocurrent, okay? All right, so now, unfortunately, to go back to another definition, what is current? Okay, current is the rate of flow of charge, if we can remember that, right? So how fast the charges are moving in the conductor basically determines how much current you will have. Okay, all right, so now let's see. Let's try to pull these things back. All right, so if you're going to use light that has a frequency greater than the threshold frequency, if you increase the intensity of that light, what are you doing? Okay, you are then increasing, right? Intensity increases the number of photoelectrons. Okay, and how does it do that? It does that because a light with a greater intensity has more photons in it, right? Which means that the number of photoelectrons is going to increase, right? Now, what does a light that has a greater frequency do? Well, a light with a greater frequency just increases the kinetic energy, right, of the photoelectrons. It doesn't necessarily increase the number of photoelectrons, and that is the difference here. Okay, so now looking at this equation, which I'm going to move because it's now blocked off. Okay, so looking at this equation, it means if we want, right, the current to increase, right, for a given amount of time, let's say time is constant, so we're now looking at this direct relationship between current and charge, right? So if you want the current to increase, it means that you want more charge that is going to increase the current, right? Which one of these statements increase the number of electrons? Well, this statement over here, okay? So which means this statement is the one that's incorrect, right? So basically what this statement is trying to say is that if you increase the frequency, the photocurrent will increase. That's not necessarily the case, because increasing the frequency does not necessarily increase the number of electrons that you're going to emit. Okay, now the last thing to check now is how valid is this statement. Okay, so this statement says, statement number 2 says that the ammeter and the current registers a current immediately after the incident light is radiated on the cathode, right? The key word here is immediately, and this now comes from history. This is true, right? Because previously, people used to think that there would be some sort of a delay, right? A time delay in terms of how long it will take for the electrons to be emitted, and unfortunately Albert Einstein proved that to be false, right? There is absolutely no time delay so long as the light, right, the incident light has a frequency greater than the threshold frequency, your electrons are emitted almost immediately, right? So this statement here, number 2, is also correct, right? So our 2 correct statements is number 1 and number 2, which means that our answer over here is going to be C, right? Option number C is going to be correct. Cool. So now let's look at November 2015, right? So in November 2015, they said, when light of a certain wavelength is incident on the metal surface, no electrons are ejected. Okay. Now, which one of the following changes may result in electrons being ejected from the metal surface? Okay, so now these type of questions get very tricky, so don't even look at the options yet. Start looking for the keywords in the statements. Okay, so the keywords here is that we're looking at wavelength, right? So the equations that we're going to look at have to be using wavelength. Okay, we have the fact that when we use a specific light, okay, that wavelength associated with that light does not emit any electrons. Okay, now we want to create a change, right, such that we can actually get electrons, right? Now, basically what you should understand here is that if no electrons are ejected, right, it means that the kinetic energy of those electrons is 0. Okay, makes sense. Electrons not being ejected is because they have no kinetic energy, right? So let's write down our equation. We have the equation that the energy, right, of the light is equals to the work function plus the maximum kinetic energy of the photoelectrons. Now, I just want to focus on this kinetic energy because they've pointed out to it over here that no electrons are ejected, so it means that the kinetic energy is 0, right? So I want to manipulate this equation and make the kinetic energy the subject. Okay, so if I make the kinetic energy the subject, it means that the kinetic energy is equal to the energy of the light minus the work function. Okay, now remember that the work function, right, this thing over here is a constant. Okay, so it's like saying it's always going to be 2, basically, right? If you want to think about it like that, it's always going to be a 2, right? So if then now you want, okay, now what do you want? You want to create a change such that electrons are being ejected. Okay, so you want a kinetic energy this time. Okay, so basically you want to have an increase in the kinetic energy, right? So if this value is remaining the same, okay, then it means that you must increase the energy of your light. Okay, so if we now take this out, so therefore we need to increase the energy of the light. Okay, all right, so now let's look at the options. The options say for A, increase the intensity of the light. Okay, now that's not going to help, right? Remember with this one, if they said that the light that we were using is not ejecting any electrons, if you increase the intensity of that light, it's not going to help you with anything, because if you increase the intensity of a light that is not emitting electrons, you are just hitting the metal with more low energy photons. So you're just hitting the metal with these photons that are weak. Okay, so A is out. All right. B says use light with a much shorter wavelength. Okay, so let's see. Over here, I'm interested in this option because it says use light. Okay, and I already have the conclusion that I need to increase the energy of the light. Okay, now let's check if increasing the energy of the light corresponds with a shorter wavelength. Let's see. Energy of light is equals to Planck's constant times the frequency of the light. Okay, I also have that speed of a light is equals to frequency times lambda. So then frequency is equals to C over lambda. Okay, so I'm going to take this now, C over lambda, I'm going to substitute it there. Okay, all right. So I now have F is now C over lambda. Okay, so this is now the lambda of the light. Okay, so what am I seeing here? I'm seeing that the energy of the light is inversely proportional to 1 over lambda. Okay, so there's an inverse proportion here, which is good because that means that if you want the energy of the light to increase, the wavelength must decrease. Inverse proportion, remember. Okay, so if you want the energy of the light to increase, the wavelength must decrease. Decrease is exactly the same word as shorter wavelength. So I think we found our answer. Our answer has to be B. Right, let's just check the other options. The other option says use metal, with a larger work function. Okay, so use metal with a larger work function. Okay, let's think about that on the side here. So the work function is equals to H times F naught. Okay, so if you increase the work function, you've increased F naught. Okay, all right, so let's see how that is going to impact. So EK max is equals to the energy minus the work function. Okay, so the work function has increased, right? So that means that if the work function has increased, you are subtracting. Remember, you were already using a light source that is not energetic enough, right? So this now becomes the constant. All right, so basically what you're doing now, because now you've increased the work function, okay, you are taking away from a value that was already a small value, okay? So which means that the kinetic energy is going to decrease even more. So in other words, basically it's going to go negative, right? Now this is now involving maths. Okay, how did I get to this negative? Well, basically before the kinetic energy was 0, right? So for this case, when the kinetic energy was 0, it meant that the energy equal to W naught plus EK. If this is 0, then it meant that the energy is equals to the work function. Okay, that was previously, right? Now this E is the same E as over here. It's still exactly the same energy. Now you've increased the work function, so you're going to then subtract from a small value, which is going to make your kinetic energy negative, right? So that's definitely not going to eject electrons, right? So you're making things worse, basically. Okay, so this is making things worse. And then increase the surface area of the metal. Okay, now that's just a dumb idea. Okay, so this one is trying to say if I was using like a small little strip like that, okay, this one, remember, already has some sort of a threshold frequency, okay, or a threshold wavelength. Okay, now if you increase the surface area, you're just making this thing bigger. Now the problem is it still has exactly the same threshold wavelength. So if already the light that we're using was not able to eject electrons, making the surface bigger is just a dumb idea. Okay. So in 2016 they said the wavelength, again, wavelength, okay, of a monochromatic light source P, right, is twice that of a monochromatic light source Q, right. The energy of a photon from source P will be of a photon from source C. Okay. All right. So if you are wondering what does this word monochromatic mean, mono means one. Okay. So basically, it's just a light source with a single frequency. Okay. So basically, it's just a fancy way to say that you are using a specific light, right, with a specific frequency and a specific wavelength. Okay. Very, very fancy word. So don't let that confuse you. Right. Okay, so now again we have to look at the wavelength, but now we first need to write down the relationship that they're telling us here. They're telling us that there's two light sources. Okay, so there's light P and there is light Q. All right, so now they're saying light source P is twice that of light source Q. Okay, so which means for wavelength, this is the relationship we have to see. Light source Q has a wavelength, okay, so wavelength of Q, right? Then for P, we need to write it in terms of Q to understand that, okay? So P is going to be twice, which means 2 times the wavelength of Q. All right, so that's the relationship that we have here. All right, so now what do we want to answer? We want to answer what is the relationship between the energy of a photon, okay? All right, so now let's write the equation. We know that the energy of the photon, this is the same thing as if I say the energy of the light, okay? These two things are the same. Okay, I'm just going to write photon to stick with the question. We know that the energy of the photon is given by h times the frequency of the photon. Okay, now remember what are we looking at here? We're looking at the variable of wavelength, so I cannot use frequency. I need to then transform this to wavelength. So wavelength we saw previously, it's just C over lambda. Okay. All right, so now recognize where the constants are. This part over here is a constant. That is Planck's constant, and that is the speed of light. So those two things, if you multiply them, is always going to be the same value. So this is a constant. Okay, it's very important for you to realize where these constants are, because it means now you can see what the relationship is. The relationship is that the photon, or the energy of the photon, is I don't want to use an equal sign, sorry, is directly proportional to 1 over the wavelength. Okay, and now remember, when we see this 1 over, it means that we have a inverse proportion basically. Okay, all right, so now what do I want to get to over here? I want to get to the fact that I need to substitute these values over here. Okay, so this statement, we can say that the energy, what are they saying here? The energy of the photon of P, okay, so will be, all right, so we want to relate it to Q. All right, so we're going to say here that the energy of Q is inversely proportional to 1 over the wavelength of Q. Right, so now let's do some substitutions. That means that the energy of P is going to be directly proportional to 1 over, now its wavelength is twice that of Q. Right, so now I wanted to make this substitution. Okay, so this 1 over lambda Q is the same thing over here, 1 over lambda Q. So what I have now is that the energy of P is directly proportional to 1 over 2 times 1 over lambda is the energy of Q. Okay, so I'm making a substitution here. Okay, so these two things are the same. Okay, so I've made a substitution for them, right? So can you see now? I can see that the energy of P is directly proportional to half, right? The energy of Q, right? So let's find the statement that says half. Let's see. A says a quarter. Nope. B says half. C says equal. D says twice. So all of these things are wrong. Quarter is wrong. Equal is wrong. Twice is wrong. So the right answer is a half. All right, now for 2017. 2017 says light of a certain frequency is shone onto a metal M and electrons are ejected from the surface. Okay. The same light source, so that's a very key word, the same light source, né? So which means that the frequency has not changed, right? So the same light source is shown onto another metal N, right? The electrons ejected from the surface of metal N have a much higher kinetic energy than that from metal M. Okay. That's an interesting observation. Okay. So basically we have a light, right? This light has a frequency, right? So keep that in mind, right? Then we have metal M versus metal N, right? Now it's said, when we take this light and we shine it on M, right, electrons are ejected. Okay, so there is some kinetic energy present. Okay, now when you take the same light, right, you take the same light and you shine it on metal N, the kinetic energy increases. Okay, can you see this? Right, so this is what's happening here. All right, so that means for the equations, right, kinetic energy, I'm going to just stop writing this max. You know it's the maximum kinetic energy is equals to the energy of the light minus the work function given on this side. Okay, let's find what is constant. Okay, first of all, what's constant is the frequency of the light. So if the frequency of the light is constant, it means that the energy of the light is constant. So this energy is constant. Okay, so it's the same in both cases, right? Because we took the same light and we shined it on M, and now we're shining it on N. Keep that in mind. Right. Let's figure out what else is a constant maybe. W naught is not a constant because the metal has changed. And remember, W naught is specific for each metal, so that has not changed. Okay. What we also know is that for metal M, this kinetic energy has increased. Okay, so now can you see if this is going to be a constant, then it means that if I have increased the kinetic energy, it means that I have decreased the work function. Okay, so for a constant value, right, think of a value, say 10. Okay, if you want the difference between 10 and some number, right, to increase, you need to take away a smaller number from it. Does that make sense? Okay, I like relating this to maths. Okay, let me write it down. So if we imagine, right, that the energy is 10, right, then I'm saying that if you want the difference between 10 and a number, right, so the difference between 10 and a number, difference is subtraction, okay, if you want this difference to increase, right, then it means that you need to subtract a smaller value. Okay, so for example, 10 minus 5, okay, is going to be less than 10 minus 2, okay, because 10 minus 5 is 5 and 5 is less than 10 minus 2 is 8. Does that make sense to you? Perfect. I hope it does. All right, so now let's go to the what do you call them? Options. Okay, that means that metal M has the same work function as metal N. Okay, no, that's wrong. Okay, metal N has a larger work function than metal M. Larger? No, 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 it can't. Like I said, metal N has to have a lower work function. Okay, so no. This word larger is a problem. No, you're wrong. Okay. C, the threshold frequency of metal N is higher than that of metal M. Okay, so now they're moving away from work function. They want to now talk about frequency. Okay, so I know there's this equation that work function is equals to H. If not, H is a constant. Okay, so which means that W naught is directly proportional to F naught. Okay, so now if I've already deduced that the work function must decrease, it means that the frequency or the threshold frequency must also decrease, directly proportional. Okay, so let's see again. So now it says the threshold frequency of metal N is higher. Okay, no, higher is not to decrease, so that's wrong. The threshold frequency of metal N is lower. Perfect. So lower means decrease, and that's exactly what must happen. So our answer here is D. All right. Like I said, 2018 does not have a multiple choice question, so this is now 2019. Okay. In 2019, they said, consider the statements below, right, regarding the photoelectric effect, right? Oh, this one looks like it's going to be easy because it's a theory question. They were very nice in 2019. They said the photoelectric effect proves that, okay, number one, light is quantized. Yes, it is, right? This word quantized means that light basically comes in discrete packets of energy, right? So each what do you call it, photon of light has a certain amount of energy. Okay, so for example, if we say that blue light has blue light of a certain frequency has 3 joules of energy, that blue light of that certain frequency, doesn't matter what the intensity is, whether it's dim or bright, it will always have 3 joules of energy. Okay, all right. Number 2 says light has a particle nature. Yes, that was the whole point of this photoelectric effect. It proved that light can act as a particle, and photoelectric effect proves that light has a wave nature. No. Okay, so other things prove this. What do you call them? Diffraction, reflection, etc. Right, those things are what prove the wave nature of light. Okay, so this one is an easy one. So we're just looking for option 1 and option 2. So option 1 and option 2 is C. Okay. Right, moving on to November 2020. Oh, where am I now? Yeah, November 2020. Okay. All right, so in November 2020, they said the sodium cathode, right, and we can see it labeled over here. There is the sodium cathode. Okay. of a photocell, and this is a photocell, okay, is irradiated with ultraviolet light as shown in the diagram below, right? The ammeter registers a reading, okay, so in other words, there is a current flowing in the circuit, okay, so if they're saying that the ammeter, oh, my current is flowing in the wrong direction. So if they say that the ammeter records a reading, it means that there's a current flowing in the circuit, okay, and that DC source is a battery which is necessary for this whole thing to work, okay. All right, so what happens in this diagram is that the ultraviolet light gets radiated onto the sodium metal, and then some electrons get emitted, okay, and these electrons are going that way, okay. They get collected here at, this is the anode. All right, so these electrons are moving that way, okay. Then they go into the wire and they move through the battery and so on, okay. All right, cool. Now let's see. They say which one of the following changes again will increase, okay. So we'll increase the ammeter reading. Okay, so now ammeter reading again goes back to current. So you want the current to increase. Current is rate of charge. So if you want the current to increase, you need the number of charges to increase. In other words, you want to increase the number of photoelectrons. Okay, so you want to increase the number of photoelectrons, and the photoelectrons are these things over here. Okay, so these things are the photoelectrons. Right, so you want more of those things coming off the surface of sodium. All right, now let's see. A says use a thinner sodium cathode. Again, that's dumb, okay, because basically if you just change the surface area or the size of the metal, you haven't changed the property of the metal, okay. It still has some sort of a threshold frequency to it, so you haven't really done anything. That's just dumb. Okay. B, increase the intensity of the ultraviolet light. Yes, that will work. Okay. Why will it work? Because, like I said, if the light source, okay, is creating a current, okay, that means that that light source already has a threshold frequency, right, which is greater than the, already has a frequency which is greater than the threshold frequency, right. So it means that if you increase the intensity of the light, okay, you shine more energetic, okay, photons onto the surface. If the number of photons are increasing, right, then more electrons get emitted as well, right. Cool. C says increase the frequency of the ultraviolet light. Nope, that's not going to work. Right, and if you want a reason for why C is not going to work, remember that the energy of your light is equals to the work function plus the kinetic energy. And like I said, sodium is going to have a specific work function, so this value here is going to be a constant. Right? Now, if you are going to increase the frequency of the wave, what do you call it, ultraviolet light, you've increased the energy of the light, which is just going to carry over into the kinetic energy. That's all that it's going to do. Okay. So it's not going to necessarily increase the number of electrons that you're going to get. The number of electrons that you are emitting are just going to move faster. That's all. Okay. Right, now let's look at the last option. The last option says replace the sodium cathode with a cathode of a lower work function. Tempting, but let's see. If you still look at this equation, right? Okay, now you need to think properly here. What is the constant? The constant is the energy of the light this time, okay? Because what are you doing? You're replacing the cathode, right? So in other words, they're saying you're still going to use ultraviolet light. So this is still going to be the same. Okay. Now, if this value is a constant, right? So let's say like 5, right? And you have now decreased the work function. Okay, so you've decreased the work function, right? So that's basically going to mean that the kinetic energy must increase, right? So if you decrease the work function, in order for the sum to remain the same value, you need to add on a more amount, right? A larger amount. So it goes back to the same conclusion as with option C. So this is just going to increase the kinetic energy of the photoelectrons, not necessarily the number. The key thing here is to increase the number of photoelectrons, okay, not the kinetic energy of the photoelectrons, right? Okay, so if we then go back and summarize, in 2014 for 1.10, the answer was C, okay? And then in 2015 for 1.10, the answer was B. And then this is now 2016, 1.10, the answer was also B. And then this one is 2017, for 1.10, the answer was D. And like I said, 2018 did not have a multiple choice question. This is then 2019, 1.10, the answer was C. 2019 is probably the easiest one out of all of these multiple choice questions. And then lastly, 2020, for 1.10, the answer is B. Okay, 2020 was also relatively not that difficult, but the options were tempting. Okay, you could have made a mistake quite easily in 2020. Okay, I hope you guys enjoyed that video. I think I will do 2018 in a separate video because already this one is quite long. Thank you so much for watching, and I will see you guys next time.